Spoštovani predsednik vlade, spoštovani gostje iz Združenih držav Amerike, dobitniki zlatega znaka Jožefa Stefana ter njihovi mentorji in sorodniki, ostali ljubitelji znanosti, gospodarstva, spoštovani gostje. Tokrat že 26. leto zapored slavimo obletnico rojstva velikega slovenskega fizika Jožefa Stefana in v tednu okrog 24. marca odpiramo vrata Instituta Jožef Stefan. Danes smo že gostili Nobelovega nagrajenca, profesorja doktorja Duncana Haldeina. Prav kmalu se nam bo predstavil tudi profesor Oussama Khatib. Poseben večer je pred nami. V njegov uvod pa k mikrofonu vabim direktorja Instituta Jožef Stefan, profesorja doktorja Jadrana Lenarčiča. Prosim.
Spoštovani gospod predsednik vlade Republike Slovenije, Your Excellency, Ambassador of United States in Slovenija, spoštovani predsednik SAZU, my warm and very special greetings goes to honorary guest Nobel laureate Professor Duncan Haldane from Princeton and to our today's invited speaker, my old friend Oussama Khatib from Stanford. Posebej pozdravljam tudi letošnje nagrajence, prejemnike zlatih znakov Jožefa Stefana. Spoštovani visoki gostje, dragi prijatelji. Danes mineva četrt stoletja, odkar smo na Institutu Jožef Stefan prvič organizirali dneve Jožefa Stefana in podelitev zlatih znakov raziskovalkam in raziskovalcem, katerih doktorati so imeli v zadnjih letih največjo odmevnost. Ali so doprinesli rezultat, ki je zatresel znanstveni svet, ali prispevali vrhunski tehnološki dosežek, ki je prodrl gospodarstvo in tam pustil svojo sled. Odbor za zlati znak, ki ga letos vodi profesor dr. Martin Čopič, njemu in drugim članom odbora se ob tej priložnosti iskreno zahvaljujem za opravljeno delo, je tudi tokrat izbral 3 nagrajence iz različnih področij naravoslovja, vetoživljenju in tehnike. Širina, od koder prihajajo nagrajenci, kaže, da kakovost ni privilegij ožjih skupin. Slovenija je majhna država, tako majhna, da večkrat pravim, da še nisem videl evropskega zemljevida, na katerem bi pisalo Slovenija znotraj njenih meja. Naš največji potencial so mladi in izobraženi ljudje, svobodomiselni, prodorni, nosilci novih idej z navdihom in vizijo. Le na njih lahko utemeljimo svojo prihodnost čez 5, 10 ali 30 let. Talentov za neizprosno raziskovalno razvojno delo je malo, a se jim v Sloveniji prelahko odrekamo. Z nespametno politiko ali nepolitiko na področju razvoja in raziskav, zlasti v času gospodarske krize, smo mnogim talentom po nepotrebno priprli vrata. Bolj ambiciozni so zaradi tega poiskali svojo priložnost v tujini, drugi pa so odšli v poklice, ker svojega talenta in požrtvovalnosti, tudi ustvarjalnega nemira, vse to je namreč potrebno, pri raziskovanju ne bodo nikoli izkoristili. Večinoma ne zavedajoč se svojih sposobnosti in navdiha. V času gospodarske krize, ko sem jo že omenil, je bila Slovenija med tistimi redkimi evropskimi državami, ki so prav na področju raziskav in razvoja najbolj skrčila vlaganja, skupaj z Madžarsko in Španijo. Vsi drugi, tudi tisti, za katere mislimo, da za nami ekonomsko in kulturno zaostajajo, pa so jih povečevali. Vsako leto se prav ob tej podelitvi zlatih znakov, spodbojen z dogodkom, oziram v našo prihodnost in ponovno prepoznavam, koliko smo Slovenci izgubili oziroma izgubljamo, zaostajamo in kako za to ni prav nobenega razumskega razloga. Po osamosvojitvi smo se Slovenci prepustili raznim ekonomističnim eksperimentom in nikoli kaznovanim finančnim vratolomnim zablodam. Nekaterih, ki vsi po vrsti vidijo raziskave in razvoj le kot postavko na stroškovni strani državnega proračuna. Eksperimentom, ki so se jasno pokazali med drugim v famozni bančni luknji. Ta nas je stala toliko kot celih 30 let abundantnih vlaganj v raziskave in razvoj. Tega jaz kot predstavnik generacije, ki ta čas obvladuje našo družbo, ne morem zlahka sprejeti. V resnici pa mladi ne potrebujejo veliko, le da bi jim bilo omogočeno, da bi lahko vstopili na pot raziskovalcev, razvojnikov in inovatorjev, da bi lahko izpeljali svoje ideje, da bi lahko udejanili svoje vizije. Zato pa so dejansko potrebna zanemarljivo majhna vlaganja v primerjavi z norostmi, ki si jih je Slovenija privoščila v svoji kratki zgodovini. Pošteno je, da ob kritiki dogajanja v slovenski družbi na tem področju povem, da se je prav gospod predsednik vlade v odhajanju, predvsem v lanskem letu osebno pričel prizadevati, da bi to obrnili. Žal pa za temeljne spremembe zdaj ni več možnosti. In naj zaključim željo, spoštovani nagrajenci, nagrajenki. Upam, da vam bo zlati znak, ki ga boste prejeli, odpiral vrata in omogočil uspešno in produktivno pot, naj si bo v znanosti, razvoju ali inovacijah. Čestitam vam za to pomembno priznanje, ki nosi ime velikega Slovenca, Jožefa Stefana. Naj vas Štefanova skromnost in veličina vodita na vajini življenjski poti. Hvala.
Hvala direktorju inštituta, profesorju doktorju Jadranu Lenarčiču. Z nami je danes torej tudi predsednik vlade dr. Miro Cerar, ki nam je svoj obisk potrdil že pred mesecem dni. In priznamo, zelo smo veseli, da ste danes z nami. Spoštovani predsednik vlade dr. Miro Cerar, prosim vas za pozdravni nagovor.
Spoštovani direktor, profesor dr. Jadran Lenarčič, spoštovane nagrajenke, nagrajenci, spoštovani Nobelov nagrajenec profesor dr. Duncan Haldane, spoštovani gostujoči predavatelj profesor dr. Oussama Khatib, spoštovani ambasador, predsednik Akademije znanosti in umetnosti, spoštovane raziskovalke, raziskovalci in vsi ostali prisotni, cenjeni gostje. Nocojko praznuje vaš inštitut, praznujete raziskovalke in raziskovalci. Ko s spoštljive razdalje opazujem vaše delo, se mi zdi, da je v resnici največji praznik, kadar pridete na sled nečesa novega, ko vas znanost pripelje do roba novega znanja. Institut Jožef Stefan ni le edinstven v Sloveniji, ampak ima ugledno mesto v evropski družini uspešnih raziskovalnih institucij. Predstavljate kombinacijo znanja, inovativnosti in prihodnosti, kar vse Slovenija zelo potrebuje. Ste prvovrstni ambasadori slovenske znanosti v Evropi in evropske ter slovenske kreativnosti v svetovnem merilu. Kot največji raziskovalni inštitut v Sloveniji ter najuspešnejša slovenska raziskovalna institucija se uspešno kosate za večjimi, močnejšimi in bogatejšimi. Ljudje ste seveda tu gonilna sila, raziskovalke, raziskovalci in vsi, ki delajo z vami v vaših ekipah in sodelujejo z vami s kolegi iz celega sveta. A dobro se zavedam, da za doseganje izjemnih rezultatov, poleg vsega znanja in truda, nujno potrebujete tudi razvito raziskovalno infrastrukturo, kot je bilo rečeno. Oboji vemo, kaj država lahko stori. Finančno podpira raziskovalno dejavnost, posodablja obstoječo raziskovalno infrastrukturo, spodbuja prenos rezultatov vašega dela na trg ter ustvarja pogoje za izobraževanje novih generacij raziskovalcev. Po veliki gospodarski krizi nam je že uspelo ustaviti trend upadanja sredstev za raziskave in inovacije. Še več, obrnili smo ga navzgor, povečali smo sredstva in s tem seveda je treba nadaljevati. Kot predsednik vlade sem vsakodnevno doživljal in še doživljam, kaj pomeni tehtanje med potrebami različnih segmentov družbe. Vedno smo prisluhnili tehtnim argumentom in kolikor se je le dalo, smo na področjih, ki smo jih prepoznali kot prioritetna, prišli deležnikom naproti. Znanost in raziskave vsekakor so eno takšnih prioritetnih področij, ki jih mora kot takšna prepoznati in pripoznati vsaka odgovorna vlada. Barcelonski cilj javnih vlaganj v raziskave in razvoj ostaja jasen. Zato si moramo skupaj še naprej prizadevati za delež skupnih javnih in zasebnih vlaganj v višini 3% BDP-ja. Vse družbe, ki so to zmogle, so danes razvite družbe znanja. Ko sem v ponedeljek zvečer v intervjuju odgovarjal na vprašanje o vlogi vlade in države pri gospodarski rasti, sem omenil znanost kot eno tistih področij, kjer so multiplikacijski učinki največji. In vaše delo to dokazuje. Vaši globalno odlični raziskovalni rezultati bistveno krepijo kakovost znanja v slovenski družbi. To pa je temelj uspešnega gospodarskega razvoja. Le dodana vrednost znanja lahko omogoči našemu gospodarstvu povečanje konkurenčnosti proizvodov in storitev, s tem pa tudi dodano vrednost na trgu, kjer je globalno konkurenčne proizvode in storitve treba znati tudi uspešno tržiti. Zato morata slovenska raziskovalna skupnost in slovensko gospodarstvo še bolj poglabljati svoj partnerski odnos. Vendar pa bi rekel, da znanosti, s tem, ko jo instrumentaliziramo v orodje na trgu, vsaj delno odrekamo njeno bistvo, ki ga sam vidim v izboljšanju kakovosti življenja ljudi. Kakovosti življenja pa ne prinašajo vedno le materialno blagostanje in podobni zunanji dejavniki. Mar ni vaše največje bogastvo in poslanstvo prav v tem, da za znanostjo vplivate na širitev človeškega duha in s tem na širitev spoznavnega in razvojnega potenciala človeka kot takšnega. Na tej točki se srečamo humanisti, družboslovci in naravoslovci in nabor raziskovalnih projektov vašega inštituta priča o tovrstni multidisciplinarnosti. Prav zaradi te širine ste resnično odgovorna družbena sila, saj znate pogledati čez in seči prek vidnega obzorja. Spoštovani nagrajenci, iskrene čestitke in še naprej uspešno in vznemirljivo delo. Čestitam seveda tudi vodstvu inštituta za vrhunske dosežke na področju znanosti in raziskav. Želim si, da vaše delo nadaljujete s takšno predanostjo in ustvarjalnostjo, da bomo tudi v prihodnje ponosni na vas in vaše odkritja. Hvala in srečno.
Hvala predsedniku vlade, doktorju Miru Cerarju. Preden pa oder prepustimo robotskemu avatarju Ocean One, mi dovolite nekaj besed o današnjem predavatelju, profesorju Oussami Khatibu, ki prihaja iz Stanforda iz Združenih držav Amerike. Oussama Khatib je prejel naziv doktorja znanosti v Toulouseu v Franciji leta 1980. Je redni profesor računalništva in direktor laboratorija za robotiko na Univerzi Stanford v Združenih državah Amerike. Njegove raziskave so usmerjene na področje metod in tehnik vodenja humanoidnih robotov. Ima naziv Fellow of IEEE. Je sourednik Springer Tracts in Advanced Robotics in sourednik Springer Handbook of Robotics. Profesor Khatib je predsednik International Foundation of Robotics Research in prejemnik IEEE RAS Pioneer Award, George Saridis Leadership Award, Distinguished Service Award, Japan Robot Association Award, Rudolf Kallmann Award ter IEEE Technical Field Award. Professor Oussama Khatib has recently been elected member of the US National Academy of Engineering. Khatib's contribution include new models, control architectures, planning algorithms and design methodologies for advanced robotic systems. His research explores the biomechanics of human motion and the brain's motor control representation of complex tasks. Khatib also worked on the development of human-friendly robots that are safe for collaborative interaction in dynamic environments, such as domestics, production, hospitals, offices, and public spaces. Through haptics and visual interfaces, he explores robot operation in remote environments to study underwater ecology and climate change, to uncover natural resources and historic secrets buried deep at archaeological site, or to perform disaster prevention and recovery operation, be it deep in oceans and mines, at mountain tops, or in space. Ladies and gentlemen, dame in gospodje, Professor Oussama Khatib, please.
Thank you so much for your kind introduction, distinguished guests, colleagues, and friends. It's really a great pleasure for me to be back in Slovenia, in Ljubljana, in this institute, to share with you some of the development taking place today in robotics. And let's see. Okay. So, as we celebrate the 69th anniversary of the Institute, there is something I also wanted to bring to your attention, that we have another important celebration that actually was part of our connection in the robotics community with the Institute. And this is the ARK. The ARK is one of the major conferences in the field of robotics that started by a young researchers some 30 years ago. We were in Udine, not far away, at a conference called Romancy. And at that meeting, there were the top really leaders in the robotic field. And this researcher, well, I'm going to disclose him now, Yadran, came to the conference and invited about probably 20 personality in robotics to come here to Ljubljana, to the Institute, and to participate in the first workshop that became a major event. You can see me on the right over there. And that meeting brought scientists from all around the world. ARK became an international meeting held in many different places. It became also a leading meeting in the area of kinematics. So we have a large number of participants, and I would like to thank you, Yadran, for what you have done to the field, and also to probably making Slovenia a major center for the research in robotics. Thank you very much. So now we go back to Ocean One. Ocean One is this amazing expedition that took us through years of development to create a robot that can somehow not only discover, find, navigate in the water, but really to capture what a diver can do in the water. And a diver not only going to see, a diver is going to do. And to do, you need arms, you need hands, you need visual feedback. And this robot is quite amazing, because when this robot reaches the bottom of the sea where human cannot go, well, we are going to be able to feel what the robot is touching. And this is through a mechanism that involves another technology we call haptics. So I'm going to tell you the story about the expedition we had on the a vessel called La Lune. But first, let me mention about Santorini and our mission just recently in last June in Santorini, going to the Colombo volcano and taking Ocean One there to explore the volcano. This was actually a part of a program, ZDF program, that took the robot to that exploration. And you can see here the robot performing some communication tasks, gesture communication between a diver and the robot. And the robot was assisting the diver with different modalities for different tasks, putting light over markers and bringing help with measurement, and also diving deep to reach and collect samples. Here is a sample from that volcano. Quite interesting, by the way. I was told not to take it or to keep it because it will be really, it will not smell very well after a few days. You have to be very careful with those samples from the water. Now, I'm going to tell you the story about our expedition on La Lune. La Lune, en français, in French, means the moon. And we literally went to the moon and get our robot to walk on the moon. But the moon is this vessel of King Louis XIV from 1664. In 1664, unfortunately, this vessel perished, and it was not discovered for many, many centuries. Only in 1993, they found the vessel, and that is thanks to the technology we have today. We have wonderful technology to discover, to see, to locate with underwater vehicles. However, that technology doesn't allow us really to do any meaningful operation. When we do those operations, we use very stiff devices, very simple, rigid manipulation capabilities. These devices are very difficult to operate. So they really couldn't take any vehicle to do those operations. And what they do is they use this suit inside of which we place a diver. Now, the diver is isolated inside this confined space, and the diver is going to dive just to be there to move the arm so that the gripper can reach an object and grasp it. Very, very different from what a diver is doing. With the hands, with the manipulation, dexterous manipulation, the human is able to do. And our aim was, how can we take those skills down to the depth where a human cannot go? Well, I mean, a human skill is necessary, while the depth human can go to is maybe 40 meters. 40 meters is far from what we have so many vessels at depth that go much, much beyond that. But also, for human, the time at which they can operate work is also limited. And also, there is a large risk. And about risk, let me show you the risk we are taking today to maintain offshore platforms. So this is from the North Sea, and we have a gas and oil platform offshore. In order to reach and maintain those platforms, we need to do something with maybe some, let me say, crazy divers. These crazy divers are going to dive to 130 meters. And to do that, they are going to use a mixture of oxygen and helium. They sit here for 1 week. They breathe the oxygen and helium, and then they go and work for another week. By the way, you can hear actually the helium.
Doit être retiré et remplacé à la main.
Tu peux passer la longue clé à laine? Tu as aussi la clé à cliquer? J'ai hâte de retrouver la surface après 20 ans.
So,
Quelqu'un veut sortir? et respirer le bon air de l'extérieur.
3 weeks.
1, 2, 3, 4, 5.
And anything that could happen during these 3 weeks, there is no way to save anyone, because we cannot get anyone out without that delay. And this is really, really dangerous. And what about going to 300 meters, 400 meters? So Ocean One came with the idea that we can do that through an avatar that is going to distance a human physically from the task, but at the same time project the human skills down there. So the concept is illustrated here with these devices, the white devices you see. These are the haptic devices we use in surgery. And now through this haptic device we are able to operate a robot, and at the same time the robot is sending signal to the device so that we can feel what the robot is doing. Not only that, when the robot is operating and when we are in a situation where we need help, we can go to another station to show what is going on, because everything now is on the cloud. The other intervention can be made when necessary, so we're able to bring more expertise to different problems. So this idea essentially is going to relay the sensory information back to the human, so the robot is a sort of sensor for the human, and at the same time project the capability of the human in the water. And through this embodiment, we are going to be able to do things that a human diver can do. So let me show you just simply how haptics work. You see here a haptic device. The operator is moving the hand. The robot is completely autonomous, except the input is coming from the human, and the sensory information is reflected back to the human. So when we touch an object, the human is going to feel it. Now, making a robot, this is a land robot, making a robot that can do this not in the air but in the water is really challenging. Building a robot underwater, there is a lot of pressure. We have to sustain the pressure, but also we have to make the robot float. But with the amazing students we have and amazing concept that we can bring together and input from industrial collaboration, we've been able to develop this robot within 3 years. And in fact, this robot is something that, like a space robot, you cannot operate it in the air. You need to take the robot to a pool. So in the lab there is no pool. We have fortunately a pool at Stanford at some distance. So we pull the robot all the way to the pool. We lower the robot through a special. And then once in the water, the robot is happy, except some functionalities are not working. We need to take it back and restart over. And little by little, this robot became capable of operating, connecting to the haptic device properly. And you can see almost a dolphin jumping like a robot. And the robot was getting ready for our archaeological mission in the Mediterranean. However, this is not a robot designed for that task. And this is what is really important about robotics. Robotics is versatile, and the capability we build can be used in many different domains. We started actually this project with the aim of developing a robot to explore the coral reefs, the environment, placing sensors, collecting samples. Through our project, we received a lot of interest from the industry to use this robot for maintenance. When we have accident, it is most of the time because we didn't done enough of maintenance, and there are a lot of difficult operation that requires many hours of diving, and that is one area where where a robot with those capability can perform continuous maintenance for many of the structures underwater. But it's not only about underwater robotics. This concept of connecting the human skills through an interface to a robot can be used in many domains. Let's think about mining. In mining, we are placing human in very dangerous environment. It's very costly. We need to bring oxygen, and we need to put cooling at those depths. And the question is, can we replace the worker with a machine and then reconnect the skills of that worker from a safe, comfortable environment? Well, I went to Peru, and this is a gold mine, and this is me under it. And what you see here in the gold mine, there is this vein, and the vein is going through the mountain through kilometers. In order to reach that gold, we blast all that chamber, and we progress, and then we take all that material up to the surface. We process it, we add chemicals, it becomes toxic, we need to clean all of that, and then all of it to reach the gold that we are after. Well, we can do much better if we were able to have a machine that will go directly just in the area that is needed, so that we will not damage the environment or put human in any danger. So this is a very important area of application. There are many other similar areas, high altitude stations where human cannot station. The idea is similar to what we are doing in the medical field, where the skills of the surgeon are transmitted to robots introduced through small incisions in the body. So we are not opening the body, and the patient can recover very quickly. So robotics today is undergoing a major transformation in scope and dimensions. And we are seeing a lot of robotics coming to human, in proximity of human. We are talking about many applications of social robotics. We are talking about the aging society and bringing domestic robotics to assist, help human. We are also wearing robotics with exoskeletal systems that can, this is one of the first operational exoskeletal system that brings support to human, where now the exoskeletal system remove all the weight and the human is just guiding that motion. We are developing robots that can be interacting physically directly with the human to assist, to lift, to do all kind of assistive tasks. We are seeing a lot of interest in service, logistics, warehouses. There is so much that we are talking about in smart cities and the new urban environment that would bring farming, that would bring vertical farming, in fact, that also would make use of robotics. The space of applications is huge. We are working with Boeing in problems dealing with confined spaces, how we assemble those wings. Do you know how they do it? They find small people to go inside. Seriously, it is so difficult because inside the wing, and in fact, maintaining the wing, changing the rivets inside, comes after these are contained with fuels. So you have to wear protective gears in order to go inside, and it's really difficult. So here are some of those examples of robotics that are bringing together human and the machine to work in close proximity. So they need to be safe, they need to capture the human intention, but at the same time they are extending those capabilities of the human. Human can be operating also at a distance when the environment is not friendly. So robotics over the decade brought much progress. much progress in the area we call mobility. That is, robots that are evolving in the air, on land, underground, in the water, to move objects, to reach locations, to navigate. But the question of robotics is not only about reaching and navigation, it's about also the physical interaction with the world. So the physical interaction with the world means that we need to bring those capabilities to the machine. Let me show you a robot we've been working with at Stanford for over 12 years. Most of my colleagues know about Ashimo. And Ashimo is an amazing machine that can run, jump, and do all these tasks. But the question is how can we get this robot to do little more than moving? How can we get the robot to interact with the physical world, to perform useful tasks, and to do it without the conventional way that we used with industrial robot, that is without much of programming? I mean, the bottom line in those problems is that if we think about this task, if we were going to use the programming of all those trajectories, we are going to end up with a large amount of effort, days of effort to program the robot. And once we change anything, we have to restart over. So how come a little child is able to do it? What is the secret? And this is what we've been trying to find. The secret is there with the skills of human that we developed. And it is a very different situation. When we are doing over and over the same task, we can afford to put the effort and costly effort to build the assembly line. The assembly line requires offline programming, and it is largely the most expensive part of manufacturing. That is programming, placing all the jigs and fixtures on the structure to make a structured environment work for that task. Now we are talking about those environments. They are unstructured environment. We are going to reach an environment we don't know exactly the location of things. There are a lot of uncertainties. So manipulation skills become critical. Now, who's else better than looking at human skills to somehow capture those skills and bring them to a robotic system? So when we move from the structured world to the unstructured world, we have to move also our modality of interaction from offline programming to planning with a sort of abstraction that allows us to give the robot higher level commands, and the robot is going to understand what those commands mean. So there is a clear separation today taking place in robotics. We had the era of industrial robotics. Now we are talking about the era of human-centered robotics. Well, those skills that we see with human brings also new challenges to the hardware, to the robot sensors, to the robot design. That is, if we look at the robots that we used in industry, these are heavy, rigid robots that are supposed to be precise, fast, and that's why we place them in cages. We isolate them from human. Well, now we have to think about new kind of robots, robots that are compliant, robots that are going to be sensitive to tactile contact. These robots are going to be lighter, safer, and these robots are essentially going to require a new design and new concepts. Well, over the years in research, we made a lot of development in those areas. And at Stanford, we worked in a robotic design that makes use of torque sensing. That design was later pursued at DLR in Germany and then was commercialized by a company called KUKA. So this is the torque-controlled based development that is essential. With torque control, we are going to be able to create compliance, to remove large part of the heavy reflected weight coming from actuation, and we then will be able to do manipulation, cooperation, performance, achievement, and also bring safety to those interactions. So let me show you another way of programming robot that our community now is using. And this is a programming that does not involve any trajectory programming. Face-to-face operation between two objects is accomplished using the reaction forces. So the reaction forces are guiding the motion properly using a human strategy. And this strategy is something that we do daily without paying attention to. So let me just show you the story of compliant motion just from Stanford work. There has been much development all around the world in this in recent years. I don't know if anyone knows this device because this is something from the past, 1981. So compliance is shown here with the sponge not deflecting as we push on the robot, with the robot moving on surfaces that are unknown, and with the cooperation that you bring between robots, and also with the cooperation and compliance with human. This is another important reactive behavior that the robot must have, and this is avoiding collision. So when we place Snoopy house, the robot is going to move around. And this, remember, this is 1981, 82, when vision wasn't available. We were still able to do amazing performance in terms of the capability of the robot to modify a path in real time. This is through a mechanism we call elastic planning. So the plan is changed in real time. Those computations are exponential in the number of degrees of freedom, very costly. This is the torque control from the mid-90s. And then we took these robots and put them on mobile platform, and this is Romeo and Juliet. Ironing, vacuuming, this is Romeo ironing, by the way. And cooperation, human-guided motion, even dancing with the robot through compliance. Then Ashimo came, and now we taught Ashimo how to also dance. Then we discover everything we are doing is inspired by the human, but is very useful for human. So we applied many of those techniques to human studies, as we will see in a few moments. So compliance is a modality that is essential for dealing with the changes in the environment, the adaptation of the robot to the environment. It is not about just recording trajectories and moving in those trajectories. Now, the problem of interacting with the world means also dealing with challenges of the assembly problem. I mean, when a human is reading this IKEA assembly, well, we go through the steps, and we manage to do it. But every step of these is really a very hard step for the robot if it is programmed through trajectories. But also, if we think about the state, the plan that we need to develop, it becomes a very complex problem. We have the tools, but these tools allow us to analyze and think about the different state of contact that we need to achieve. And once we went we go through all these different steps, the computational cost is quite high. So one approach we have been using was to observe human and see what human strategies we have that can be used as the operation through which we are going to do the planning. So in order to really reach the contact information and the tactile perception, we close the eyes, and now we are going to perform a task of face-to-face, for instance, and we discover a lot of the strategies that the human is using. They relate to center of compliances attached to the object and the relationship that we are going to perform. And using these, now we can perform tasks. We change the grasp. We don't know exactly where the object. The robot is going to grasp it. We push the robot, and the robot maintains the contact, even if the contact is moving. This is a piece we're placing on a model of 787 Boeing wing. We disturb it, and the robot is going to search its way without changing the program, and it's going to find the location. We disturb it again, and the robot will find back. So the robot is not relying on trajectory, relying on relationship and skills of much higher level. Working on many different tasks, observing the robot and trying to teach the robot. But trying to teach the robot not the trajectories, trying to teach the strategy behind all these trajectories. And here is an example of a segment where the robot is putting the cap on the bottle, and the student is changing configuration, and using the compliance, the robot is able to perform this directly without having to plan any trajectory. We show the robot how to put the teapot lid, and well, the human is having problems with it as well. Well, but it's easier for the robot. So anyway, what is really the message here is the connection between human and the machine are essential. Humans have so many skills, and our machines are becoming more sophisticated with sensors and capabilities, degrees of freedom, arms, and body motion. And we are developing algorithms and techniques for controlling those systems through our inspiration from the human. But these algorithms and techniques are valuable to analyze human motion as well. Recently, Springer Nature and a group of us organized a summit on life and robotics, looking at these two major angles of the connection between a human and robots. Life and robotics looks at the knowledge that we bring to designing machines that capture capabilities of human, to create interaction, and to look at all the different aspects of impact, the social impact, and all the results that we can obtain. Now, that means we are going now to, if we really want to interact with human, we need to understand human motion. And this is something that your institute has been working on for years. And we have been pursuing the work in the area of human movement and human motion, looking at characteristics that we study for robots. It turned out humans make use of the mechanical advantage to reduce the muscular effort. Here is a Stanford athlete, it's a Stanford athlete with injury, shoulder injury, and we are going now to reconstruct the motion. To reconstruct the motion, we need an accurate model of the musculoskeletal system. Most musculoskeletal systems are obtained from cadaver. So what we tried to do was to go further, because we really needed more details on the upper body musculoskeletal system. So we used the MRI. we scan with MRI, and then we segment and we obtain very accurate models that are very important in those studies that we are performing. Anyone plays golf? No? Do you need any help? Yeah, but because now we know the secret. I mean, somehow, by observing a human and studying and applying the metrics, we know the secret. They are related to the fact that you should not imitate. So in golf, don't imitate anyone. You need to fit it to your own physiology. And we have our own atlas of lines of acceleration that could inform us how to move and how to perform the motion. In fact, there is this connection, and one idea is to, so you will wear sleeves, and those sleeves will just give you the directional corrections needed to improve. And this is very important in injury prevention, in rehabilitation, in many, many different aspects. We are pushing this even further to trying to understand how the brain, how in the brain motor control is taking place. What kind of representation humans have of the environment of the task. Now, as you know, in order to look at the brain, you need to go inside MRI. But inside MRI, you don't have space to do any meaningful task. So we use haptics again. So you see a screen inside MRI where so you cannot put a haptic device inside because, well, it's magnetic, but we bring the haptic outside and bring the action to inside, and now from a distance you are able to interact physically to perform meaningful tasks. And now we have data from the brain and from the physiology to connect the two, the action and the representation, and we are finding amazing things. Yadran and some colleagues in robotics, you know about the Jacobian that connects four torques to resulting forces, and what we are finding is there is a neural fitting of the Jacobian in the brain. And this is really remarkable. That is somehow the human, when we learn, we capture those models of our body, of the tools we are using. And these are things that you wouldn't think about unless really you make those interesting connections and bring those tools. Now, we talked about compliant motion, but human in daily life, we use so many different contexts. It's not only one object that we are placing, but our body is in contact with the environment, and we have to perform multiple compliant motions. Now, that means we need really to address all of these and understand the models that would allow us to control compliant motions at different locations. Contact with the environment is very difficult. In fact, if you go to a show of Ashimo, they tell you there is one rule with Ashimo: don't touch it. If you touch the robot would fall. You interrupt the trajectory. So we broke the rule, and now we can guide Ashimo to making contact, to sit, to move, to be guided. If you look closely, you can notice how Ashimo is surprised. What's going on? We need to teach Ashimo also to avoid collision. Don't touch my hands. And the robot moves the hands. Say, don't touch my hands. And the robot moves. So when we think about the amazing capabilities humans have in doing things, like just cleaning a window or taking an object, involves so many things. We are bringing controls to many aspects of that motion. We are controlling our posture, we're controlling the task, we're controlling the contact, we're controlling the constraints, the obstacles. And we are doing this in real time. And for robots to do those computations in real time, it's very hard. But human studies help us understanding how this could be done using the human strategy, and we developed techniques called constraints-consistent whole-body control that allow us now to control the robot, to make contact in the physical world in real time. I'm going to show you a simulation of a robot making contact with moving surfaces that are slippery. We represent those with friction cones. So let me show you. And everything is moving. This is really, really difficult for any machine, even for a human probably. And any time any of the red forces goes outside of a friction cone, we will fail. And the robot is able to maintain this while everything is moving. So we are now ready to climb. We can do climbing because if we are able to maintain and balance all the contact, then we can explore stable contact. Oh no. I mentioned that this could happen, and it happened. Let me. Yeah, it seems like it is fine. No, it's not fine. So it is not fine. So it is okay. I'm going just to have to restart the PowerPoint, but while I'm restarting and while we are waiting for it, I'm going to take some questions. So I don't know why Microsoft doesn't work well with Apple machines. There is something. I'm not saying they do it in purpose, but so we just restart and it should be fine. Yes, please.
You are talking about degrees of freedom. What is the state of art in number of degrees you can deal with? Like thousands of millions?
Yeah. So today's, industrial robots use between 4 to 6 degrees of freedom. I mean, to position and orient an object, we need at least 6 degrees of freedom, and this is saying, yeah, I don't know why it is not restarting. Just 1 second to make sure that we start. So, but today's robot, like if we take Ashimo has about 30 degrees of freedom. So when you are going with exponential computational complexity, going from 4, 5 to 30 degrees of freedom is huge. But when you think about the problem of having 2 robots cooperating, the problem becomes really bigger and bigger, and this is the challenge. And this challenge is growing as the complexity of the task is requiring more degrees of freedom and more cooperation between multiple robots. So you don't want to build a big, huge robot to carry things. You bring cooperative robots so they can fit in the environment. And okay, I think we are getting there. All right. Perfect. I have to complain to Apple. All right, it's coming. So another important thing about human is the use of tools. I mean, we developed our intelligence through interaction with the physical world, and we discovered tools could allow us to perform many different things. And one of the things about those humanoid robots, is that they are designed to move indoor in flat environment, and when the environment is uneven, it becomes difficult. So we developed techniques to go from biped walk to triped to quadruped, what I call supraped, where the robot is now able to move and step, find a contact, and then increase the support area. And now we can go into those challenging environments with a robot that is biped. Biped is really useful because it has this integration of all the functionality in a small volume. So what we do in robotics, we have this model that brings action. So these are the actions the robot is going to perform. And they are relying on the perception from the sensory information. So the interaction with the world is going to bring back feedback, sensory information that is processed. And this processing is complex. We abstract, we go higher and higher. Here we have higher goals that are broken into action that the robot is going to perform. So what we have been doing was to create more modalities that allow us to control the robot full body, whole body, at much higher level, using skills coming from descriptions that the human is sending through programs or physical interaction or haptic interaction. At the same time, the data that we are processing is going to be relayed to the human, and we relay only what is needed for the context of the task. So this interface and this environment is actually in the same place. That is, this is a loop. And this loop is taking human descriptions, high-level human descriptions, to a program that is breaking them into actions, relying on the skills the robot has learned to perform those commands that would allow us to accomplish those complex tasks. This is a very general approach that can be used for many different aspects of robotics. We can classify robotics in these broad three domains: field robotics, so underwater, mining, space, health and wellness, everything that is related to interaction with human, direct interaction with human, and also all the implications in Industry 4.0 that relates to more flexible interaction between the robots and the environment, not through structured environment. And this is the third area. So in those areas, at the center, we have core research methodologies that are common to all these different areas. And this is really one of the things that is special about robotics. Robotics brings a multidisciplinary knowledge need in order to develop these different potential applications, and that requires people from humanity all the way to engineering, and going through the medical and the physical therapy and all the people who are involved in contact with human. So at Stanford, actually, we are developing now a new center that will bring people from the different disciplines to work together in a common space, in environments that is the environment that you want to bring as close as possible to the reality. So for the underwater, we will not have to pull the robot anymore to the pool. We will have the environment in the center. For mining, we will have that environment. And all of these things are bringing the development to Ocean One and to the capability of extending the reach of a human to domains that are dangerous unreachable, difficult. So just few technical words before showing the video about the expedition. The idea of this robot is not like to take a manipulator and attach it to the robot. The idea is really to create a robot with the design concept of a whole body. And the whole body concept is something that we don't think about too much, but humans have that model of macro mini structures that is illustrated here between the body of the robot and the hands of the robot. And we can see it in many operations. In order to achieve faster dynamics, we need to deal with this coordination between the body and the arms. And we can see in this example here how the human is able to reach, and then at the same time the whole body is still moving. This is very typical in space docking. Building a robot with the optimized workspace to achieve this, so the docking, we stop the hands and the arms are bending to take out the inertia of the body. This is very important. The dynamics of the robot is changing with configurations as the robot is moving, and all of that is optimized to achieve the characteristics so that the robot can perform those tasks. The robot is full of sensors, navigation capabilities, and oil-filled arms to make sure that we can go and dive. And through testing and through experiment in the pool, there was a day I remember it was a Tuesday afternoon. I told my student, tomorrow we're not coming back to the pool. We took the robot, we put it in a box, and we ship it to France to land on the André Malraux, this scientific boat of the Ministry of Culture, responsible for archaeological mission underwater. The robot arrived, and here is the robot on the André Malraux. Now, imagine, this robot went diving 1 meter, and we are going to take the robot to a field test at 100 meters. Some people told me, this is not going to be easy. And in fact, we really were really worried about this. But the robot didn't. The robot just went in the water. We were reasonable, by the way. I mean, here we took the robot only to 15 meters. At 15 meters, we could rescue the robot. We could send a diver and rescue the robot. But first, we wanted to check all the functionality of the robot, and the diver was with the robot. This is, I believe, Olivia. You can see Olivia from the camera in the chest of the robot, and Olivia certified the robot. Everything is working. So we came back and the next day, and we took the robot to the site of La Lune, and we went diving meter by meter. We were so worried, and the robot all the way reached the bottom. And here you can see 2 cannons from La Lune. These 2 cannons are still standing on the surface. And our colleague archaeologists located this vase, and they thought, well, we should maybe try to get this view and capture the vase, and this would be fantastic. What we forget, and this is how field experiments are important, what we forget is that as we come closer and closer, the thrusters are going to raise all the sediment, and now we lose visibility, and suddenly our robot gets caught under the cannon. And it was around midnight, and the captain started to say, Oussama, we have to leave. The sea is dangerous now. We have to leave. And we were trying everything possible, pulling the thrusters back, pushing, tilting. Nothing was working. And suddenly you see why we have a human form, why we have arms on this robot. Because now our navigation, pulling the robot, wasn't going to do it. But if you think about it through the embodiment, you think my elbow is stuck. If you push, this is going to come out. So we literally walked on the moon, and by pushing with the haptic device, the robot jumped. And I was very happy. So the next day, the weather was bad, as the captain said, so we couldn't go. The day after, the boat had a problem with the power. But finally, on Friday, the 15th of April, we were on the site very early in the day. And what is nice, once you have collected the artifact, you place it in a container, you close the container, and the container autonomously will come to the surface. And here is the treasure coming, and this is something that is apparently not only unique, but it came up without any scratch, and the archaeologists were really, really happy. They very often they try to collect anything, and it is broken. It is because it is very difficult. These are my students excited, and this is Olivia, the archaeologist. She immediately said, "This is coming from Catalonia," and this brings me to something you were talking about this morning. You were talking about the mug, the coffee, and the loving cup, and the Californian loving 3 cups. Well, this is 4. The Catalan vase. So this is from 1664, untouched, and it came in one piece. And I'm going to ask you to tell me, after so many centuries, who is the human who touched it first? All right.
Okay.
So we're deploying now the robot in the water for the first time. The water is salty, different from the pool water, obviously. But the robot was very happy because, in fact, the salty water makes the robot float better. And we had to do some balancing, but the robot was fine. And here is the robot at 15 meters near Marseille. And Olivia is checking the different functionalities. The coordination between the arms, the grasp, the hands. The hands had to be tested, and these are special hands that has only one motor, and they go with the shape. And Olivia is saying, "You're fine, you can go," and I'm not going with you. So now we're going to dive for the 91 meter on La Lune, and this is the control room involving our colleague archaeologists with the engineers. It's very dark. The robot is going down. We put already light down on the ship, and you can see the robot coming from the top.
Oui, tu y es presque. On est en train de revenir sur zone là. Tu y es presque.
The sediments started to come as we came closer and closer.
On y est là.
Pas plus loin, pas plus loin. Revenez pas par là. Stop.
Stop. Too late.
Que là, il faut faire
And
Attention, tu tapes le canon. Tape le canon bleu.
60 cm.
look at Hannah, my student. She was, oh my God, what's going to happen? So now with the haptic device, trying to push with the arms on the surface, on any surface.
Oui.
Can you put your hand like this and go?
So this is the Friday 15th when we were diving for the second time, and very quickly we relocated the vase you saw, and now we're grasping the vase with the two arms holding the vase to stabilize it, and now we're taking it to the container.
Okay, perfect. Pas mal, on l'a.
Non, il n'y est pas encore, il n'a pas posé.
Il a lâché, il est dedans.
Oussama, tu peux fermer le couvercle avec le bras.
Asking me to close the cover. Landing on the moon. It was quite amazing. The mission was really also amazing by the fact okay, you can see who's touching it first. All right. So this is Michel Lourd, the director of DRASM, the archaeological center. Champagne for everyone, including the robot. So it was quite also amazing. The 2 weeks later, when we had the press conference in Marseille at the museum, the response, everyone wanted to come to the museum to see the robot with the press corps, and we had to leave the robot back there. But also, what was really remarkable is the connection with the band we made with our colleague from archaeology. So we went like 2 different groups with different understanding of problems, and we came back as one team. Thank you very much for your attention.